Pagano and Goro principles of biostatistics. Okay, so probability distributions. We first need to understand what's meant by a variable. I'm sure many of you understand this already, but I'm going to start at the beginning. So, and also what is a random variable, which can assume different values or states. And we use the theory of probability to describe the distribution of random variables. So variables basically are things that we're interested in a research study, and they're called variables because they can vary. So examples we all can think of, like age, gender, calorific intake, health status, and so on. You can think of many yourselves. When we say this, it's a random variable, we mean that it's subject to random effects and can randomly vary. And now, a variable can be quantitative or qualitative. Now, there's only a one-letter difference, I think, between these. No, two-letter difference between these two words. Quantitative, quantify, means to actually measure, whereas qualitative is a quality. And the other thing about variables is that it can be an independent variable, also known as a predictor, explanatory, or exposure variable, or it can be a dependent variable. That is, it's a response or an outcome or a criterion. Those are other words that are used. And basically, the dependent variable is believed to depend upon the independent variable. But quite often in studies, it's not clear which is the independent, which is the dependent. Maybe they both vary together, and one isn't causing the other one to vary, but they may have a common reason for varying. So types of quantitative variables, they can be discrete, and these only occur in whole numbers. Like, for example, the number of children in a family. You can only have 1, 2, 3, 4. You can't have 2.5 children. You could have a mean of 2.5 for a country's mean family size or something, number of children. But the actual numbers in a family would be discrete. And then there's continuous variables, and continuous can basically have any value and depends on how accurately you can measure them. And if a scale has a true zero, then this is known as a ratio scale. So someone who is twice the height of someone else, that is a ratio, and you could have, although not in practice, you could have zero height. Anyway, the measurement that we take in meters, that does have a zero. So that would be known as a ratio scale. There's also ordinal variables, and this is where the measurements are ordered in some way. So they may not be measured precisely, but they are ordered. Good example is what's used in questionnaires. You have to say how much you agree with a statement. So medicine is fun. How much do you agree with that? Is it strongly disagree, disagree, neither agree nor disagree, agree, and strongly agree? So it's a scale from 1 to 5. But if you gave a 4, that doesn't mean that someone else who gave a 2, you're twice as keen on medicine as that person. So this is a different scale. It's an ordinal scale. And you can't actually talk about it in ratio terms. Okay, I'm sure you all have 5 for this. Okay, categorical variables. This is categories, and the simple one is the binary variable. This is where we have 2 options, such as gender, male, female, alive or dead, healthy, diseased. There's only one of these 2 options that can apply. And you can have more than two options. Obviously, like a country, there are many countries in the Middle East. These could be categorical variables. This could be a categorical variable. Or hospitals, let's say hospitals in Riyadh, that would also be a categorical variable. We can categorize quantitative variables and turn them into, so we're turning quantitative into a categorical, but it's because we're doing that, it's actually an ordered category. It's a bit like ordinal. So for example, we could say that if the family size has got more than 3 children, that would be large. If it's less or equal to 3 children, that family would be categorized as small. Similarly with birth weight, you could have a baby, if it weighs less than 2.5 kilograms at birth, then that would be considered low birth weight. So it's either low or normal. Okay. And for BMI, you could do the same. So you can do it for lots of things. So we have here a BMI range, anything less than 15, this would be very severely underweight, up to 16 to 18.5, this would be underweight, and then normal, and then we go into the 3 different obese classes. If you're over 40, it would be obese class 3, and so on. So this is an ordered category. It's worth remembering that when you're talking about real data, actually, because our measurements are always rounded, they're not precise. So let's say I was to measure someone's height, I wouldn't be able to measure that precisely. There's always going to be some error, and I wouldn't actually be able to get the exact number. So we always round, we put into categories. So basically all our measurements actually, if you like, are kind of the categorical data. But we assume that they are normally distributed, not normally distributed, we assume that they are continuous on a continuous scale. So we assume that the numbers can, let's say the heights that I'm measuring, they can be any value at all, precisely. Okay, so probability distributions. There's 2 different types. There's empirical and theoretical. So an example of empirical is when we collect data, and this is the latest data from the USA on the age distribution for deaths from COVID-19. And so you can see that the distribution is skewed. So this is actually negatively skewed. So what we see, as we all know, is that older people are more likely to die. And these are frequencies. You'll see these are numbers here on the left, this vertical axis. And if we consider out of the total number of deaths, these would be the same as the probability. So this is like a probability distribution. So empirical means real data that we've collected from a study. Compare that with theoretical distribution. This is where we have a formula, like for the normal distribution. If we know what the mean and the variance is, then we can plot this distribution, which is the normal distribution. And there are many different distributions that you can theoretically define and plot. Okay. So probability distribution for a given random variable can be displayed in a curve or histogram or a table, and we can use a formula to calculate it. So the probability of a random variable, we would denote that as a probability for x, a random variable. Okay. Someone want to say something? I think if you want to ask questions, I'm happy to take them. If you want to stop me, clarify, just let me know. Okay. Otherwise, probably best to mute your microphone so that we don't get interference. Okay, so sickle cell trait. This is known in the Middle East and in countries that have malaria. This is a problem. Let's consider this. If we have offspring from a man and a woman and they're both heterozygous, so A and S, A is normal, S is sickle cell disease. So there's heterozygous, so that the offspring then would have from each parent a half chance of having sickle cell disease gene. And so from both parents, the probability that the child is sickle cell to be homozygous would be 0.5 times by 0.5 gives us 0.25. So this we will call probability P. And the probability of not having sickle cell is just 1 minus 0.25 is 0.75. So if the parents are heterozygous, then the offspring have got a quarter chance of being homozygous sickle cell and a 3/4 chance of not having sickle cell. Okay, so in this example, it's binomial, it's binary. You either have it or you don't. And the two outcomes are mutually exclusive. You've covered this in the previous lecture with Dr. Hassan. For example, the birth of the child is either male or female. That's also mutually exclusive. In our example, the child either has the disease or it doesn't have the disease. Okay, so let's say we have a family of 4 children. What's the probability that none of them, one of them, 2 or 3 or all 4 have got sickle cell disease? I've given you the probabilities in the previous slide, so quarter and 3/4. So here we think of the sample size, the size of importance here is n, and this is 4. So we've got 2 parameters that define the binomial distribution, n and p. So here it's 4, but we could have chosen 10 or whatever. And the p is the probability. In our example, it was 0.25 probability of having sickle cell. Okay. So, all right. So we're going to denote having the disease as D and not having the disease as H. And specific values we can denote lowercase d and h respectively. So the probability that none of the 4 children are sickle cell, SS, is going to be 0.75 times 0.75 times 0.75 times 0.75, or 0.75 to the power of 4. And if you work that out in your calculator, you get 0.3164. So that's pretty easy, isn't it? What about the probability that exactly one child has got the disease? Okay, so that means the remaining children are healthy. So one child has got the disease. What's the probability of that happening? You might want to think about that. It's slightly more complicated than you first think. What we need to think about is where that child can happen. It could be the first child that is diseased and the remaining 3 are not. Or it could be the second child, or the third child, or the fourth child. So these are the possible outcomes or scenarios for getting one child having a disease, the remaining 3 children in the family being healthy. So these sequences represent all the possible birth orders, and then we can work this out as being 0.25. The 0.25 is for the probability of having the disease, and of course there's 3 of the 0.75s here, so it's going to be 0.75 to the power 3. Okay, so then when we work this out, because there are 4 ways of getting this result, we need to multiply this by 4. So it's going to be 4 times by 0.25 times by 0.75 cubed gives us 0.4219. Okay, so what about for 2? Well, you'll see there's actually more ways of getting 2 children having disease. There's 6 ways of that happening. And so each of these combinations has a probability of 0.25 squared multiplied by 0.75 squared. Then we've got to multiply that by 6 to give us, and when we do that, we get 0.219. So about a 5th chance. What about for 3 children being diseased? Well, there are actually 4 possible combinations here. So it's going to be 4 times by 0.25 cubed times by 0.75. And that gives us a small number, less than 0.05. And finally, what about for all children being diseased? Well, this is actually quite a small probability. It's going to be 0.25 to the power 4. Okay, actually, I can show you this in Jamovi, and we'll be doing this tomorrow. Let me just see if I can show you here. Now, I'm running the 1.6, which is the latest version, but you could also run 1.2 something, which is the solid version. It works for both. What you need to install is this module here, and you install it by going to here and going to the library, and here it is, distraction. So it's already installed for me. It's called distraction. So if we click on this, and it gives us various different distributions, but we want the binomial distribution. What's happening? Okay, here it is. Right. So, all right. So let's see. Our sample size was 4, and our probability was 0.25. I'll just press enter, and it works this out. And here's the distribution of outcomes. So then we can work out probabilities of getting 0, and that probability, so 0 children having the disease, gives us 0.316. It's the same as what we had in the slides. And then for 1, do that, we get 0.422, which is quite a big chance. And then 2, a smaller chance. And then 3, and so on. So we can play with this. And it also shows where the distribution is here, so you can see this plot. Okay, so that's basically, we'll be doing this tomorrow as well. Let me get back to the slides now. Okay. So, yes.
There's a question in the chat.
Question. Sure.
Someone is asking, is 4 the number of possible combinations?
Yes. 4. In the previous slide? What do you mean? Here? So where we've got, it depends on how many children are diseased. So if there's no children diseased, then there's only one combination, right? And same if they're all diseased. Okay, so here where we've got all the children, probability that none of the children have got sickle cell, they're all healthy, is going to be 0.75 to the 4, but there's only one way of getting that, okay? But as soon as we have 1, then there's 4 ways of getting it. But please ask.
Yes.
Have I clarified?
Yes, hello, doctor. I was just asking, so as for this example per se, so the probability of having the disease is going to be 0.25, and then healthy is 75. And then the number you multiply before that is going to be the number of possibilities. So here we have 4 different possibilities. We multiply it by 4. Okay, thank you.
Okay, that's correct. And so you'll see when we get to to 2, there's more ways of getting 2, because we could have first 2 diseased, the middle 2, the last 2, and then first and third, second and fourth, and so on. So there's 6 different combinations there. Okay. So I just wanted to show you that actually these numbers that we get here for the number of combinations follow something known as Pascal's triangle, which is quite a clever triangle. So if we start off with 1 here, and then below it, what you do is you sum what's above. So here there's only 1, so this is only going to have, this is only going to be 1. You'll see on each of the 2 sides of the triangle, it's always going to be 1 because there's only 1 above. But as soon as we get to the next layer here, we've got a 1 and a 1. And then when we get to the next layer here, this is going to be 2 because that is that 1 plus that 1. Okay, when we get down here, it's going to be 2 plus 1 gives us a 3, and the 2 plus 1 gives us a 3 here. And our particular situation is here, where we've got 4 different, n is equal to 4, and we've got 1 possibility where when there's 0 that are ill, and then 4 that's 1 ill, and 6 where there's 2 ill, and 4 where there's 3 ill, and 1 again where there's all 4 ill. So this comes from Pascal. So if we had 5 children, then these would be the numbers that we would use, and we would multiply our probabilities, the powers of the probabilities by these numbers: 1, 5, 10, 5, 1. Okay. So in our example, this is where we've got the number of combinations, like from Pascal's triangle, 1, 4, 6, 4, 1. So if there's 0 that are diseased, then that's going to be 1 times by 0.25, because to the power 0, which is actually going to be 1, multiplied by 0.75 to the 4, that gives us 0.3164, where we've got 1 diseased, and then that will give us, that's 4 combinations multiplied by 0.25 to the power 1, that's just 0.25, multiplied by 0.775 to the power 3, gives us 0.4219. So these are just the numbers that I've shown you in the previous slides. So I'm showing you this, why? Well, these are all the possible outcomes. And in your last lecture, hello? Was there a question? Okay. In your last lecture, there was a sample space for numbers of students that were taking so many statistics maths courses. Do you remember that example? And what the probabilities were for students taking either 0 courses, 1 course, 2 courses, or more than 3 courses, 3 or more courses. And we have the probabilities on the right-hand side, and they added up to 1. It's the same here, because these are all the possibilities, okay? They will all add up to 1, right? So they're mutually exclusive, and these possible outcomes, whether you have 0 or 1 or 2 or 3 or all 4 children that are diseased, those are mutually exclusive outcomes. Then those probabilities, they all will add up to 1. If they don't, then you know you've got a problem with your calculations. Okay. So I'm going to explain this thing here, which is the combinatorial formula. And what we've got here is just the number of combinations multiplied by the probabilities. Okay, so this is to show you, actually this was done in R, which is like Janovi, and it just shows you what we've seen. So with n is equal to 4 and p is equal to 0.25, these are the probabilities. So for 0 it was 0.3 something, or 1 it was 0.4 something, and so on. And to get all 4, very small probability down here. Okay. So what we could do is actually increase the probability. Let's say it was for boys and girls in a family. How many boys? Then the probability, although it's not exact, for boys and girls being born is almost 0.5. Let's say it was 0.5, then this is the theoretical distribution that we would get. Okay, if we were to collect data on births of children according to their gender, then we could get an empirical distribution. This is a theoretical distribution. So what you can see here is that we've got a symmetrical distribution. Okay, and let's say we increase p further to 0.75, and this is actually the distribution for children who are healthy, actually, isn't it? And you'll see it's skewed the other way from what we had in the previous slide. We could increase.
Excuse me, Doctor.
Yes.
There are some students that are asking that they cannot hear you properly. Could you use a mic, please?
Right. Well, yeah, maybe I've got the AC on. I'll switch the AC off. Right. Is that better? I don't have a mic, so I'm using my laptop, which has a built-in mic. Is that better?
Students, is that better? Could you please write that?
They're saying yeah, it's better.
That's better?
Yes.
Okay. Thanks for letting me know. I'll try and speak more clearly and loudly. Okay, so we could increase the n, okay, the size of the family in our example. So if we had an n is equal to 10, then and same probability of 0.25 as in our sickle cell example, then this is what it would look like, okay? This is the probabilities for the possible outcomes. So 0 children, 2, 4, 6, up to 10 children being ill. So the probability of 10 children, all 10 children having sickle cell, you can imagine, you can try and work it out, it's going to be a very small probability. Okay, so let's say we increase the sample size further. Okay, so we've gone from n is equal to 10 up here to n is equal to 20 down here. Then what you notice, I think, is that we go from a kind of skewed distribution here to a more symmetrical distribution. So as our sample size increases and the probability remains the same, then what we see is a more symmetrical distribution. Compare that with n is equal to 4. If we go back to the previous slide here, you can see this is really quite skewed and not symmetrical. Okay, so we need to make assumptions for our binomial distribution when we do a binomial calculation. We've got a fixed number of trials, n, and each trial produces 2 mutually exclusive outcomes, success or failure. In our case, it was disease or health, and these are known as Bernoulli trials. The outcome of each trial is independent of other trials. Okay, that's important. And the probability for success is constant for each trial. That's pretty much the same as saying that they are independent. Okay, so combinations. The calculation for binomial probabilities uses a formula for combinations, and I showed that a few slides back. And this is what it looks like. And many calculators have got a combinations on there. You'll see Basics calculator will have a button for combinations, which allows you to do these calculations. Okay, the exclamation mark here means factorial, and I'm sure you've seen this before. And basically, if you've got n factorial, that means n multiplied by n minus 1, multiplied by n minus 2, and so on until you get down to 1. So, for example, 4 factorial is going to be 4 times 3 times 2 times 1 gives us 24. you've got to remember that 0 factorial is equal to 1. Okay. So n factorial gives us the number of ways that n items can be ordered. So for n choices, the first item we have n choices for the first item. For the second one we have n minus 1, and then for the third item we have n minus 2. And then we need to multiply those because for each of these we have successive combinations which we multiply together. Okay, so let's say we've got 3 items A, B, and C. We can order them as ABC, ACB, BAC, BCA, CAB, CBA. Those are all the possible combinations, okay? And there are 6 of them, and this is the same as 3 factorial because we've got 3 items. Okay, so this formula here, it's also given as ND in some textbooks. So this is the same. And if you think of if you do this for combinations, 4 and 0, for choosing from 4 to get 0, then you just put this into the formula and you've got 4 factorial over 0, 0 factorial, 4 minus factorial. So remembering that this is equal to 1, what you end up with is just 24 over 24 gives us 1. That's a situation where we have 0 that are ill. And if we've got 1 that's ill, then it's going to be this. When we work this out, we get 4. And then for 2 ill, we get 6. And someone is drawing. Okay. We've got 3. We have 4 combinations, and then if all 4 are L, then if we work this out in the same way, we get 1 again. Okay, so, yeah, okay. I guess I'm going to have to stop people from doing stuff. How can I do that?
Doctor, you can make me co-host so I can look into that.
Okay, how do I do that?
Just right-click on my name and make a co-host.
Okay. So I made you host, is that correct?
Co-host.
Co-host.
Yes.
I can make you host.
There should be an option for co-host as well.
I only see make host.
Right. I don't think you should do that because this is on your account, so I don't have a subscription.
Okay, well, we're just going to have to put up with people drawing and scribbling. Maybe they can add.
Doctor, if you go down to your screen or if on, oh yeah, okay, so Shoaib, you're the host now, so you can just go to the top of the screen more and then disable annotations.
Ah, this one, okay,
Yeah.
Thanks. Okay.
You're welcome.
Right, so I've shown you that you can do this in Jamovi, the distraction module. Okay, so you can look up in Pagano, Appendix A has got probabilities for binomial outcomes. Okay, so we can compute summary statistics for the binomial distribution from its parameters. Remember, the parameters are the number of trials n and the probability. So the mean, for example, is going to be n times by p. Okay, that's quite easy. And the variance is going to be n times p multiplied by 1 minus p. And there's a maximum here of when p is equal to 0.5. So the variance is maximum at 0.5. You can experiment with this. If you change p to 0.1, what happens? You find that the variance is larger. Okay, and the standard deviation, I'm not sure you've done this yet. Yeah, you should have. Okay, it's going to be the square root of the variance. So it's going to be the square root of np multiplied by 1 minus p. Okay, so in our example, the mean number or expected number of sickle cell children in a family of 4 would be 1. It's going to be n, which is 4, multiplied by the probability, 0.25 gives us 1. And if we work out the variance and take the square root, we get the standard deviation of 0.866. Okay, so if there's more than 2 outcomes, then you would be dealing with a multinomial distribution, which is just an extension of the binomial distribution. So I'm going to now move on to the normal distribution. And this is some old data from more than 100 years ago, where they measured the heights of male criminals. And you can see this distribution. I've already talked about symmetry. This is a quite nice symmetrical distribution, and it's known as a normal distribution. Normal because many variables are normal. They are distributed in a normal way, so it's a pretty normal type of distribution. So height is a good example because our height is determined by many things. Lengths of many bones, genetic factors, all sorts of things affect nutrition, early experience, and so on. So it's interesting here. Okay, this is 6 foot. Nowadays, there are a lot more men that are 6 foot or over. Back then, there were fewer. The actual UK male average, because this is UK data, in 2007, the male height is about here. So you can see that they were a lot shorter in those days compared with now. However, men were still a bit taller than the average height for women. The average height for women in 2007 is shown by this red line. Okay, I showed you previously, this was on Jamovi, when we've got n is equal to 4 and p is equal to 0.25, the example that we did. We have specific outcomes here, 0, 1, 2, 3. They're discrete outcomes, okay? It's not on a continuous scale. However, we often think of something like height as being a continuous scale, and because the number can be any number, there's an infinite number of values in between any 2 numbers that we care to choose. Okay, so this is a very common distribution. It's also known as a Gaussian or bell-shaped curve. It's unimodal. Unimodal means it only has one peak, and it's symmetrical about its mean. Okay, so the mean is represented by mu and specifies the center of the distribution. The standard deviation is represented by sigma, small sigma, this thing here. These are both Greek letters, and that specifies how much variability or dispersion there is around the mean. And these are both population parameters, mu and sigma. Okay, so these can be used to completely define a normal curve, and if you have the formula for the normal distribution, you could plot a very nice normal bell-shaped curve like this. Okay, so what this tells us is that values near to the population mean are more likely to occur. Of course, there are some people who are very short if we're measuring height, and some people who are very tall. Okay, but if we look at everyone in a population, it will look something like this. And if we select a person at random from the population, they're more likely to be near the middle, near the mean, than in the tails. Okay, so these are mu and sigma. What are they? Are they population parameters or sample statistics? Anyone going to say?
They're saying parameters.
They are parameters, population parameters. I said that already, and they use Greek letters, whereas sample statistics, like X bar for the mean, they use Roman characters. Okay, so many biological random variables of interest to us, like blood pressure, cholesterol level, height and weight, they're approximately normally distributed, but none of them are exactly normally distributed. So we always need to remember that we are approximating. We can often use the normal curve to estimate probabilities with these variables. Okay, I think, just trying to think, I think I might stop here and carry on the example, because I'm going to go through a particular example. We're going to get locked into this particular example. So in this lecture, we've covered the binomial distribution and the normal distribution. And tomorrow we're going to go through particular examples. And in the lab, we will also, I'll give a sheet, I'll be distributing a sheet for you to do in the lab. We'll be using Jamovi. If you could install the modules distraction that I mentioned, and also RJ, you'll need those two modules to do the practical tomorrow. I think I'll open the floor. So are there any questions anyone has on what I presented today so far?
Someone is asking if you could recommend materials to practice problems.
Well, at the back of the textbook, Pagano, there are examples. There's plenty of examples, and there are answers as well. And you won't be doing examples tomorrow, so you'll be able to see.
Is there any more questions? Someone is asking, is lab going to be on campus tomorrow?
Yes, I will be on campus tomorrow, so I will be there physically, and both the lecture and the lab I will be taking in lecture room BG68. So for those students who can attend, I look forward to seeing you then.
Right. Someone is asking, is it for all of them or not? I think, Abdullah, it is for certain people that I have to attend for this week. I think
yes.
5.
Correct. As I understand it, Mr. Muntasa, he has selected people who can attend lectures for different weeks. So whoever can attend this week will be attending tomorrow.
Any more questions, guys? Right, I think that's it, Doctor.
Okay, all right. Well, thank you very much. I look forward to seeing you again tomorrow. And I will just stop this recording.